The only way to truly avoid sample bias is by using a random sample. So the random sample concept, a simple random sample that we're going to look at right now, we abbreviate this SRS, and we do talk about simple random samples a lot, so you'll see this SRS come up from time to time. This is what it refers to. In a random sample, each individual of the population has an equal chance of being selected, regardless of other individuals. So we'll take, for example, if we were to put the names of all US states in this hat, and then mix them up really well in the hat and draw out an SRS of size 4. And we usually use lowercase n for our sample size, so I'll just write this as SRS n equals 4. I'm going to draw 4 state names out of the hat. And let's choose Montana. We're going to pretend that I did this in a hat. Texas, I actually did this on a website and generated a random sample. Florida, and Ohio. If all 50 state names are mixed up in that hat and I draw out 4, this is a simple random sample. Anything that makes knowing one of the outcomes affect the outcomes of others would not be considered a simple random sample. So things that people do, like a quota sampling technique, for example, things that people do to try to force a sample to be representative go against randomness. And that's why those things are often, in the end, not as good. So for example, if I said, let's choose one from the West at random, one from the South, also at random, one from the East Coast, and one from the Midwest. We'll just assume the Southwest is in one of these. If I were to break them into these 4 categories, I might feel like I was going to get something that is more representative because I'm deliberately spreading them out, but it would be no longer random. This would not be a simple random sample if we impose this constraint. And in our sample, we can see Texas and Florida both pretty much qualify as South, but we did get some spread in our sample. Now, it can be tempting to try to serve as a randomness generator yourself as a human being and say, I'll just look at the map and I'll choose a set of 4 states that to me feels very random, right? If you do this, most likely what you're going to generate is something much more like what we talked about here. This is what a human being who is trying to act random is most likely to do. So this is what human bias would bring in. And we can look at that human bias now by returning to that first day demographic survey where each person was asked to select a single-digit random number, and we can see what people did. Now I am looking at results from a previous semester because I'm recording these before the current semester students have had a chance to enter them. But you can still pull up the results from your current semester and see what students have done. So to get to this, I'm going to go into Blackboard, and under week 1, we have under section 1.1, view the results here for our demographic survey results. This is going to bring up the Google Sheet that has all of our results. If I scroll over to the right, number is at the very end. This is a list of the random numbers generated by students. I am going to select this whole list and create a graphical display so that we can see what this looks like. Okay, I have generated a histogram here, which we'll talk about a bit more in Chapter 2. But for now, we can probably understand what this is telling us pretty well. We had very few people giving us a number around 1. We had only one person give us something between 0 and 2. 6 people gave something between 2 and 4. 8 people gave us something between 4 and 6. And a whopping 19 people gave us something between 6 and 8, right? This is very common. It turns out people think 7 is the most random number, right? So what we do as humans when we're trying to simulate randomness is probably 5 is the first thing that occurs to us because it feels very neutral. It's not too far to the left, it's not too far to the right. And then we say, well, 5 is too obvious. I'm going to move it just a little bit off center, and we all naturally gravitate a little bit towards that 7. And this is why humans cannot be trusted to simulate randomness. We all think way too similarly to one another to generate anything that has the characteristics of randomness. What this graph should look like if we had truly been generating randomly is something that is approaching a consistent bar height, what we would call a uniform distribution, right? A consistent bar height straight across. So these examples here are from computer-generated random simulations, and they illustrate that certainly a lot better than what we were looking at. Now at n equals 50, which is both of these here, we didn't really establish that nice level pattern yet. There's still a lot of natural variation just due to luck. But we can see that as that number gets bigger, so over here we're looking at n equals 1,000, it's much closer to what we would call uniform because all of that random luck has kind of averaged out. So this is something that you will see happening in general in this course, is with larger samples, we get a lot of that natural variation due to random chance just smoothed right out, right? And as we know from what we just looked at, ours was not random at all and looked much more like this, where this here is 7, right? And we had lots and lots of people saying 7 is the most random number. Now this does bring up some important questions because when we start talking about things like presidential election predictions and polling, the names in a hat method is not really going to see us through, right? If I say all voter IDs, that's how I could get a list of all registered voters. So let's take all voter IDs, put them in this hat, and then start drawing our SRS of 1,000 here. And 1,000 is the number. Sorry, that was an unexpected little interruption from an iPhone somewhere in this house. We take an SRS of 1,000 for these polling predictions, and 1,000 is fairly common for these. It gets us a 3% margin of error, which we'll talk about more in chapter 3. But if we take a simple random sample of 1,000, clearly all of these numbers are not going to fit in this hat, and if we were to attempt to do something like this, we couldn't physically mix them very well. So what we really use is computer-generated random sampling, as we're going to look at next. Take, for example, this list of 7 Warner Brothers cartoon characters from when I was growing up. Perhaps for this generation these names are not so familiar, but they would be familiar to anyone of my generation. We're going to choose a simple random sample of size 3 using the Google Random Number Generator. And to do this, you need to perform a Google search on the words random number generator, and you'll see a generator at the top of the search listing. So I'll type in the words random number generator and hit Google search. This gives me a generator here right at the top. I have only 7 names, so I'm going to change my max to 7 and hit generate. And I can see that 1 is my first result. So I'm going to write down 1. I hit generate again and I get 7. Now you're all witnessing this. I didn't cook this. We've already seen 2 extremes as our first 2 random choices. I hit it again and I get 6. Now, if you were to get a repeat, like if I keep going, say I get 7 again, supposing I wanted a bigger sample, you would just throw out all the repeats and keep going until you get 3 distinct values. I have just generated a simple random sample of 3 of these characters. So number 1 is Bugs. Number 6 is Mickey. And number 7 is Pink. This is my simple random sample of 3 characters. Of course, even this isn't very efficient if we're talking about something like a list of all voter registration numbers. So let's look at something a little bit more realistic that happens with, say, for example, applying for school transfers. When it's all done by lottery and a wait list is generated, we would use something like a spreadsheet program for this. What we're looking at here is the same list of names where first we have the lists in any order. And in this particular list, they are, as is often the case, alphabetic by last. There's a function in Excel called RAND, and you're not expected to do this in this course. I'm just telling you in case you're curious. This function RAND, with no arguments in its parentheses, generates a random number between 0 and 1. It doesn't matter what the bounds really are of the number. We just want to make sure that they're all done consistently. So this function generates a random number between 0 and 1, and that's what these numbers here are in this list. Now what we do is we take the whole list and we sort it by rand. And what we have here is what we would call a random sort. Once you have your data in a random sort, you can just start pulling from the top of the list, something that feels completely deterministic, the opposite of random. The behavior now feels not very random, but it is still generating random samples. So I could get my simple random sample of size 3 just by taking the top 3 on the list. So here's my SRS, my simple random sample, with n equals 3, using this method instead of the Google random number generator. One advantage to this is that it also gives us a random sort going forward. So if this were something like a school admission lottery, we would have not just the ones who initially got in, but also a waiting list generated by the random sort going forward.